Okay, so just to let everybody know, I've started a recording. Any questions or anything will be published in the recording of this meeting. This is the TFA Tech Forum for TFA. As I mentioned, the agenda items are firmware configuration, firmware update by Manish and Maduka. There's 2 sets of slides to be presented. Without much further ado, I'm going to stop sharing and hand over to, I think it's Maduka. You're sharing yours first, aren't you?
Yeah.
Okay. I should have stopped sharing. Please take it away, please.
Do you see my slides?
I see your slides.
Okay, awesome. Hi, good morning, everyone. Yeah, this is Madhukar. I'm part of the Trusted Firmware A team at ARM. I'm from Austin, Texas. I really apologize for the delay. So this discussion is about the firmware enhancements that we are planning through leveraging the FConf framework. If you remember, Louis gave us an update a couple of weeks ago about how we plan to leverage the firmware configuration framework to make some improvements and enhancements to Trusted Firmware A. Since it's necessary to have some background information about FConf, I'm going to give a very brief introduction to the firmware configuration framework. By no means this is an exhaustive discussion, but if you have any questions, please let me know. So FConf stands for Firmware Configuration Framework. We intend it to be an abstraction layer in which platforms can access their platform-specific data in a scalable fashion. A developer can access a property without actually knowing how the property is being stored. Typically, most of the properties we either store as in a C structure, and many properties we retrieve from the device tree. So the idea is to abstract away how the properties are being stored, and the framework gives an API for the developer to retrieve the information in runtime. Typically, if there's many of the platform-specific information is stored in appropriate device trees. As you can see, one such a device tree snippet here, which gives the information about the UART standard output serial node, such as the clock frequency, the base address, which is captured in the reg property. So the FConf framework works on the concept of populate functions. A populate function is essentially a mechanism through which the platform can retrieve the information about a specific property in runtime. As you see here, populate UART config is one such function which retrieves information about the configuration information of the UART device from the device tree. The populate function is also expected to fill that information into a C structure, and in runtime later, the accessor API provided by the FConf can help the developer to access the properties. So, to be implementation specific, as an implementation, we have chosen C structures to store the intermediate values of the properties. The developers are given access to the properties using a standard API called FConf get property, and the property has to be specified by using the namespace, subnamespace, and the property name. The namespace loosely refers to a collection of a large group of properties. One such namespace is hardware configuration, which talks about the existing devices in the platform, such as timer, intercontroller, UART, I2C bus, and etc. And subnamespace refers to a small group of related properties. As we see here, UART configuration refers to one such subgroup, and the API gives you a way to hierarchically access a specific property. For example, we see here FConf get property to get the base address of the URT. FConf framework leverages several pre-processed macros to do the magic underneath the framework. The FConf get property essentially translates to a pseudo function where it basically concatenates the namespace and subnamespace, and the platform integrator who is responsible for creating the accessor for creating the populate function will also be creating the macro. As you see here, the hardware config getter function will give the access to the appropriate property in the C structure. The idea is to abstract away the mechanism to access the platform-specific data. Using the API, we intend to we intend to make the driver to be platform independent. For example, a common URT console driver can be used across multiple platforms without depending upon the static information of for the base address of the URT or the baud rate or the clock information. The API can be used to retrieve that information in runtime. So the firmware, the configuration framework requires each populate function to be registered with the framework. We give a macro to help the developers to do the same. It's called FConf register populate macro. What happens underneath is the macro essentially registers the callback function and creates an entry in the linker script. And at runtime, each bootloader image for a specific platform has to invoke the FConf populate API. What this does is this helps. This essentially iterates to all available callbacks, I mean the populate functions, and invokes them by providing the right inputs to the populate functions. For example, to retrieve the URT information, the populate function has to be given the address of the hardware configuration device tree. Apart from that, we also associate every populate function to a specific configuration. The reason is because in any particular bootloader image, it is possible that there could be more than one device tree, and a specific populate function can only work with one specific device tree. So we use the configuration type identifier to make sure the populate function is invoked on the right device tree. So the framework expects the populate functions to succeed and return a value of a non-negative value. If it happens that the populate function cannot retrieve the appropriate property from device tree, either because the device tree is not well populated or if a property is missing, then the callback is expected to return a negative value. And the framework handles this and panics because it knows that a mandatory property is missing from the device tree. Note that all the properties are populated into the C data structures during the initialization phase, much before the control is passed to the next bootloader image. So we intended to use the FConf framework to make some improvements to firmware TFA bootloader images. One such idea was to move away from statically configured pieces of trusted firmware and leverage the FConf to retrieve such information in runtime. So the idea is to make the static components into at least a little more dynamic. A good example would be the IO policies used by the underlying platform and a chain of trust descriptors, as well as the hardware configuration of the various underlying devices. The idea is to move away from the hard-coded compile time structures of macros and move them to the device tree and retrieve them in runtime using the FConf framework. We believe this can help us to reduce the source code fragmentation among a set of compatible family of platforms. If you see now at the present, we have a lot of header files even for ARM platforms to describe some platform specific information like the base address of the global the gig generic interrupt controller, the base address of the distributor or the redistributor. So the idea was to put all that to transfer all that information into device tree and later retrieve that information in runtime. This can help to make the appropriate device driver or the library, for example, the gig widget driver, to be commonly used across the compatible family of SOCs. Um, the end goal being that we would have a common bootloader image for a set of platforms. For example, if a ARM platform can stick to certain properties and specify them in the device tree by following the device tree bindings guideline, then we could probe them in runtime and use the common device driver. So we have started evaluating, trying to move the static configurations into dynamic configurations, and we have chosen many such existing components in TFA to do that. For example, we have done that for the SDEI, software delegated exception interface. The events, the private events, and the shared events earlier were described as part of the platform-specific header file, and now we have actually moved, for at least for the ARM platform, for the FEP platform, we have moved them into the device tree. So the idea is this can help the common library or the device drivers to be reused across multiple platforms so that they can be made more robust. As you can see here, on the left is a header file snippet, which shows the private and shared event descriptors for every event, such as the event number, the type of the event flags. This information is very specific for each platform, and each platform exports this information such that the TFA can actually initialize the SDI driver. As we see, we have actually moved this into the device tree, and as of now, there is actually an SDI device tree binding defined in the Linux. As we see, it's the device tree property of SDI is very much similar to what we have defined in the header file. It's very in a very intuitive manner, and we have written, created a populate callback function, which retrieves the information about the private events and the shared events as part of platform initialization of SDI. And in the SDI driver, we leverage the accessor API to retrieve the information about each event. So we have also identified some other components in ARM TFA platform port to be made dynamic. We have specifically picked the FEP platform to study the feasibility of this effort. At this point of time, we have made the platform UART configuration to be dynamic, and some of the patches are actually in review. We have all made the platform topology to be dynamic, the configuration of the GigV3 driver, the timer, the SDI event descriptors. Manish will be showing shortly about how he plans to move the chain of trust descriptors to their device tree. And Louis has already made a patch for transforming the static IO policies into the device tree. The end goal here is to align with the total compute roadmap of ARM, where we want to reuse as much of software as possible to make the performance as better as possible on a particular device compatible to the trusted compute specification. So this is still a work in progress, and we have received some comments in the TFA mailing list. So as of now, the FConf framework is still experimental, but we're working on making it more robust based on the feedback. In the future, we also are planning to make the setter API. It is very much similar to the getter API. The idea is to update the right to the properties in runtime such that another consumer can actually get the updated property value. So we are also working on making the FConf robust by putting necessary checks at appropriate places for performing bound checks to make sure we catch any corrupt device tree or ill-formed device tree. And we plan to use this session to make any design decisions and discuss with the wider TFA community. And yeah, we are looking for more inputs from the community. That would be all from me. Manish will be sharing his presentation. Any questions?
Question. Hi, Varun here. Varun Wadekar from NVIDIA. Can you guys hear me?
Yes.
Yeah, so just some questions. If you want me to ask them at the end, I can also do that. But just initially, I just wanted to understand, we already have device trees, and on top of it, now we are trying to add this one more layer. So I'm not, I'm struggling to understand the intent still. If a platform is just using the device trees, isn't it already it's not using static configuration. It's already using devices, and then at runtime they can always read through this. So, so what is the advantage of using FConf here?
I can give a simple example. So, for example, yeah, we do have access to device trees in every bootload image. But if a particular device driver module wants to access a property, then it has to start all the way from accessing the device tree and look for the compatible property and retrieve the information and all those things. And of course, this would be a runtime overhead. But on the other side, if all the necessary properties have been already queried and retrieved from the device tree, then every new call to access the property will have no overhead at all, right? It would be like reusing the access. And we also intend to standardize the configurations across more platforms. For example, the chain of trust. The idea is to reuse as much code as possible. I don't know if that answers your question.
Can I add to that?
Yeah, sure.
Yeah, so correct me if I'm wrong. The way I'm thinking about this is it's sort of like how DTBs are exposed to the Linux kernel, right? So you've got the same kernel image that runs across all platforms, and all your customization for the platform comes from the DTBs, right? So in effect, I think in the long term, it would be like you have the same TFA image for virtually all platforms, minus some platform customizations, but most of it would be the same and then just customized through our device tree. Is that a fair statement?
Yeah, exactly. So the end goal is to have a common bootloader image.
So the total compute.
Yeah, so can I add one more thing?
Yeah.
So this is Sobi Matthew. So one thing we have to keep in mind here is device tree is not mandatory for all platforms. There might be some highly memory constrained systems where we cannot use device trees. So then the trouble is, how do you support such platforms where you don't have device trees, plus you have platforms where you have device trees. So you need an abstraction which will remove the direct access to device tree, which is what the FConf is trying to do. FConf gives you the flexibility to have statically defined properties if you wanted to, but also use DTB as a backing store. So the current backing store is a C data structure, which means you have the option of compiling it statically if you wanted to, if you're memory constrained, or you could populate it from a device tree. And device tree is not the only format that people and platforms are interested in. There might be other formats. In the UEFI world, they have a different format. So that the motivations for this new abstraction on top this FConf.
Okay, yeah, thanks, Obi. Actually, yeah, that helps with the context a lot. So, so thinking about that, I just had one more question. So does this Now adding of FConf to the mix, does it impact boot KPIs in any way on some platforms?
So if you see the FConf design, it's meant to be as less invasive at runtime as possible. That's why it's macros instead of functions, right? It resolves. So if you have a C data structure, it resolves to the C data structure directly at compile time. So there is no overhead involved at that point. So it was designed to keep all the overheads to minimal as much as possible.
Right, but then the C data structure would still have to be populated from the device tree, and my assumption is that it would happen at boot time. Is my assumption right, or no?
Device tree anyway, if you had a configuration inside device tree. So that time is, that hit is there if you go with dynamic configuration anyway. Now, for a statically compiled platform,
Is
that's
anybody
where.
else losing Sobi entirely?
Oh, sorry. So is it audible now? Is it better? Hello?
It's breaking a little bit.
How about now?
Voice is a little better.
Okay, I think what I was trying to say is for dynamic config, you always have the hit of reading the device tree. So if you have dynamic configuration, you have to read it at some point. Now the difference comes if you're moving from a statically compiled configuration to dynamic configuration. So that's a platform decision whether they want to move things to total dynamic description, or if they care about KPIs and if they want fast or small efficient image, they can still stick with static description. So that's a choice left to the platform. Was that clear?
Right, yeah. And if we stick with static configurations, then with the introduction of FConf, then does that mean that we now have to create those structures by hand, whatever FConf is expecting, since we have our own ways of storing some static information?
I don't think so. So the original intention was you're reusing the same data structures that were there previously.
Okay.
So the generic code still is compatible. We are not breaking compatibility here. So we are still using the same data structures, but they are being abstracted through FConf. And ideally, we shouldn't have breakage, but I'm not sure. We might have some cases. I'm not sure about that.
Yeah, I don't expect anything to break. For example, we have made the GigVT driver, and we have used weak functions actually to implement. We have implemented some strong functions to override the base addresses of Gig. If the FConf is not supported, for example, in scenarios where we enable reset to BL31 IME flag, then we use the static information.
And by static information, you mean the current configuration knobs that are already present. Like, for example, for SDEI, you have all the different macros hash defined.
Yes, exactly.
So those will still be live. Okay.
Exactly. So, so the macros still exist, right? For example, the macro which takes 3 arguments to define event still exists. We don't change that. But how we are just populating those event descriptors in runtime. That's it. The macros will continue to exist.
Right. And this would be, so is there some timeline until which they will exist, or they will exist, indefinitely? So I'm just trying to understand,
we're not, so we're not going to take away the static capabilities to describe a particular configuration. FConf is like probably an enhancement, and platforms are free to choose that.
Sure. Okay. Got it. Thanks. I don't have any more questions at this point.
Yeah, I see. For example, you have described an SDI patch for NVIDIA platform, right? If you use the FConf, I think it could be done in a very similar way that FVP platform did it.
Right. No, I was just trying to understand if, if there is a timeline involved, and so, do we have to plan for that transition? But it looks like we don't have that timeline in place, so which means platforms can take their own time to transition.
So one other comment, right? So despite having the FConf abstraction, even though you have the same BL images, your FIP image for each platform will still be different, right? So it might be worthwhile to look into see if there's a way to get away from that. Right? I think that'll have some security implications, but I think that'll help to go more towards this Linux kernel model where you're separating out the DTB and the TFA images or the BL images.
Yes, I think that is the goal we would like to reach to, where you have one firmware image which is validated and properly tested, and it runs well without any SIP extensions in the binary itself. Yeah, but it's a journey, given that different platforms have different constraints. But if most capable platforms can migrate to this framework, I think, yeah, that should be possible.
Right. Again, the solution to that is again like having modules, right? Like how you have kernel modules. Yeah, you can potentially have BL modules that load itself. So every ARM platform can start off with the same BL1, BL2, whatever image, and load your platform customization for modules. Of course, it's long term, but I think it's worth having that in mind as you design it.
Yeah, I agree. Yeah.
So, okay, let me start over here. Thanks, Madhukar. I'm Manish Badark. I'm working from Cambridge office for ARM. I joined a few months back in ARM office. So, so the basic motivation over here, as Madhukar explained, like we are using the FConf framework for the various kind of things. So here I'm explaining like how we can move the TBBR caught information using the FConf framework into the device tree. So let me start it with this. So the main agenda here I'm covering is like a basic overview of the authentication framework, which is currently in place, and we are using it. And the current design of the TBBR code descriptor, how exactly these descriptors are placed in the code and how we are using it. And then we will go to the how we can use the FConf for this code descriptor and move it effectively into the device tree. So the basic authentication framework, which is implemented in the trusted framework, it contains all these modules. So we have the generic module and the IO framework, which is in place, which is used to load the image. So when the authentication is in place, then these modules do the extra work of doing the authentication of the images using the authentication module, which is over here. And and this platform port, like every platform has to give the caught information, which I will cover in the next slide. So every image has one caught information. That caught information, the platform has to give it to this generic code, and this generic code can use this caught information in order to load the image effectively by authentication. Also, this platform port provide the provision in order to get the in order to send the root of trust public key if it is queried by anybody, and in order to authenticate the image. Basically the root nodes which don't have any public key are getting authenticated with the root of trust key. So which is the most authenticated key which is in place in the platform. And platform have their own methods in order to provide that root of trust key. And then we have the various modules in place which are taking part in this authentication verification. So if you see over here in the blue pictures, like there is an image parser, there is a crypto module, and there is an authentication module. So authentication module basically like provide the abstraction APIs in order to call some functions from the image parser and crypto module. So image parser module basically provides the APIs in order to extract the information from the certification image. So the certificate image basically consists of like signature algorithm and hash information. So during the time of authentication, whenever the authenticate module need this information, he just queried it to parser module and get that information. And the crypto module, like we are using the embed TLS over here, like some APIs to verify the signature and verify the hash accordingly, the which authentication method that particular image getting used, we call this function. So if it is a hash method, we call a verify hash. If it is a like signature, we call it as a verify signature. So these APIs are already in place, and these are in the libraries. So we have the chain of trust like this in our code in current case. So all the images which are present in the FIP, like, so those are placed into this code descriptors, and these code descriptors are having the again some kind of set, if you can see over here. So suppose if I want to authenticate the bootloader image, so I have to authenticate first this trusted boot firmware certification, and that is again get first authenticated by the root of trust key. So we have to provide this linkage properly uh, uh, in this particular array so that we can extract that information and go to that authentication process. So this may be the chain, may be the very small also, or it may go like this also. So if it is any non-trusted image, we have to go to the non-trusted OS firmware content certification. That is again get authenticated by the non-trusted firmware key certification, and this has to be authenticated by trusted key, and trusted key has to be authenticated by root of trust. So this all the chain information is being provided over here, and it is getting extracted statically in the current case right now. So let's go with the one example, like how exactly this chain of trust for one particular image is being provided. So if you see the BL31 image, which is in order to authenticate this particular data image, I have to authenticate all these images first in order to authenticate BL31. So basically we have to authenticate all the certificates. So this certificates basically contains either the hash information or the public key information. So whenever we authenticate this content certificate, that means this BL31 hash is getting authenticated, and it is now trusted one, and that we can use it in order to authenticate our BL31 image. So basically this hash is being provided to the crypto module, and then he calculate the hash out of this BL31 data image, and calculated hash image getting compared over here, and if it is matches, then this image get authenticated. And the same case happened for all the certificates over here. It may be either hash or it may be either signature, so depend upon the authentication method that particular image being used. So just to give the brief overview how the code descriptors for the certificate and the raw image in our code looks like. So if you see Okay, so if you see over here, like this is the trusted boot firmware certificate, and we are providing over the image ID, image type, and the parent of it. So parent here, it is provided as a null because this particular certificate is being authenticated by the root of trust key, and this particular certificate provide the information of the hardware config hash. So once this particular image get authenticated, it grabs the information from the certificate and put that information in this particular buffer. So whenever this raw image, whose parent is this boot firmware certificate, uh, he go and grab this hash information from here and provided it to the crypto module, and uh, then this particular image get authenticated accordingly. So one thing to note over here, like in order to grab the information about the hash, we have something like hash ID, hash OID, that is object ID, which is present in the certificate image, and that is being provided by this particular descriptor. So if you see here example like hardware config hash, uh, here we are providing the uh, from where exactly we have to grab the information from the certificate. That is hardware config hash ID. It is nothing but one kind of string only, and that information is given over here uh, to this image, and this image will accordingly grab that information and put the data into this hardware config hash buffer. So if you go to some complicated uh, more kind of linkage, so we have example of a BL31 image which I already shown over here. So this particular image again it is again basically all the data image are being authenticated using the hash methodology, and all the certificate images are getting authenticated using the authentication method as signature or the anti-rollback, that is the NV counter. So this one, if you see, this parent is SOC firmware content certificate. Hence, to validate this particular image, we have to validate first this SOC firmware certificate image, which is again point to the SOC firmware key certificate, which is mentioned over here. And again, this particular image get validated using the trusted key certificate, and trusted key certificate is being validated by root of trust. So at every point of time, whenever the certificate get validated, it puts either the hash information or the key information in this particular buffer, which can be used by the next image in order to proceed with the authentication. So this is what I have already mentioned. Each image is having its own image ID, either it is a certificate image or raw image, and we have to provide the parent of that particular descriptor, like which is being used in order to grab the key information or the hash information. If there is no parent, then that image is directly being validated using the public key, and we have to provide whether that particular image is a raw image or the certificate image. So raw image in the sense like, for example, all the bootloader image, which has only the data part content, and the certificate image is nothing but we have the X501 standard certificate image, which contains this hash and public key information. And we have three different kind of authentication methods available. One is the hash method, one is signature, and one is the anti-rollback. So if you see in the anti-rollback, we have two kind of anti-rollback methods, OIDs are available, which are trusted one and non-trusted one. So these OIDs can be used in order to grab the NV counter from the certificate image. and that can be get compared with the counter from the with the NV counter which is present in that platform. If this NV counter is having the higher value, then only we can proceed with the authentication. And I mentioned like previous image, like this authentication data is being used when this image get authenticated. We grab the information about the trusted world key, or in this example, trusted world key and non-trusted world public key into this particular buffers. And these buffers are getting used by the next image in order to go ahead with the authentication. So this is what the all about the authentication framework, which is in very short. Already documentation in brief is present in the PFA firmware. You have any questions over here? Okay, okay, let me proceed further. So as I mentioned, like this certificate and the image descriptors, which are very statically placed in our code in this fashion in the array, and we are using this array very statically in the code. So the main motivation why we want to use the device tree in order to get a read of this static stuffs and put in some readable format these all certificates and raw images, and get that information in the code and form the structures runtime. So I come up with this particular like approach, and where we can provide all the certificates and in this format. So suppose if it is like a particular, if it is a root node, I mean these certificates get validated by the public key root of trust. Then we provide it as a root node, and then we provide the p handle for this. So this p handle is basically used in order to get that image ID in our code. So p handle are used in order to get the information about the image ID, and this image ID, this parent's image ID is being passed to the another image if they need it. So in this particular case, if you see, the raw image is using the parent as this boot firmware certificate ID. When it is a root node, we don't have to provide the parent over here, and we don't need to provide any authentication method and authentication cookie, because this image anyway is getting authenticated with the root of trust, and so we already have the information about it, and we can just go ahead and do the authentication with only two parameters like root node and p handle. So but if it is having some parent, then we have to go ahead to provide the authentication methods over here. Like in this case, we are providing authentication method as a signature and authentication cookie. That means the OID information which is getting used by the certificate to extract the signature. And we have to provide the anti-rollback cookie. So as I told, like we have two kind of OIDs for anti-rollback, which are trusted NV counter and non-trusted NV counter, which is getting used in order to extract the NV counter. And with basically this anti-rollback method is only used for the certificate, and it is not used in our raw images as of now. So the main intention of parsing here is like we first parse all the raw images and form the structures out of it. And what are the parents over here mentioned? We go to the parents and and we fill the necessary information in the parent over here, and then we again parse all the certificates and fill the full data structure, and put all this data structure again in the similar kind of array over here, and then it can be again seamlessly we can use it as in our code. So this diagram shows like how we are populating the TBBR code descriptor from the device tree. So again, as Madhukar mentioned, we are using this FConf register populator function in order to populate the in order to call our populate function. So we have to register it with the populator function, and when this function get called, we will do this operation of the filling of the structure and making that particular array, which can be used later on by the load image function in order to load and authenticate the images. So the pros of this particular operation is like we can add seamlessly with the proper chain of trust information in the device tree. So device trees, we can extend and add the information over here, over there, like which, and we can provide the linkage properly over there, and it should work by the parser in the code. And it also helps to add the descriptor in the more readable format. If you see in the code, currently the descriptors are descriptors are present in the structure, but not in that readable format. But if we go to the device tree methodology, then we will get to know what exactly each property do, and it will add more readability to this code descriptors. And definitely we can avoid using any static initialized buffer and descriptors in the code. So we can take that out. So I'm planning to make like a separate file for this one. If somebody want to use the FConf, they can directly use this file and populate all the code descriptor and create it at runtime. Yeah, and the cons is over here. Yeah, definitely we need to allocate the more memory statically. We don't have any provision to make it any dynamic memory in the trusted firmware. So we have to go to the worst case and provide all the static memory in any worst case. So maximum number we have to provide for the descriptor and allocate that much of the memory before doing any parsing. Any questions?
No, but I do have a comment. I said it might be a long-term goal to separate out the DTBs and have a common BL image, right? I think that should be a more near-term image, because this again, right? As long as this is tied to a platform and everything is tied together in a FIP, right? Mm-hmm. I don't see the motivation to move to FConf. Because there are still going to be different FIP images for different platforms, right? What you've really done with FConf now with this is moved the problem from tables in code to tables in a different file, right? I think its real value will show when you have the setter API and when you split the DTBs out from the FIP, so that all platforms can have one BL image FIP.
Yeah. Sorry to interrupt.
Oh, no, that's okay.
Yeah. If you see in the currently, so many platforms which are TBBR compliant are using the same code descriptor mechanism. So it is being adopted by so many platforms already. So this code, whatever I have shown, like array of descriptor, is being common to most of the platform as of now who are TBBR compliant. So in that case, like this can become like a common thing, right? Is that answer your question?
Sorry, I dropped off. I'm sorry. Could you repeat what you were saying, Manish?
Yeah, so I mean to say this particular array of descriptor, which are common across many platforms as of now, like we have only tbbr.c file, which is being compiled with many platforms, and everybody is using that one. So it is again depend upon which image they put into the FIP. Accordingly, that particular code comes into the picture and do the authentication process, right? So but in the worst case, we have to provide this much of the memory, but nobody is stopping like deleting or adding uh, provided this particular range.
All right, yeah, I understand that. All I'm saying is, yeah, if I was making any decision, I wouldn't move to FConf unless I would separate out the BL images from the DTBs, right? Otherwise, whether these tables are in DTBs or in the code, right, does not make as much of a difference, right?
Yeah, so
Because
only
you still need a different image for different platform or every variation of the platform. Right?
Yeah, so I agree that different image will be there, but they may be having some image ID available with that particular image. So still they can form the cart over there and provide that information via device tree.
Correct. So I guess let me put it another way, right? So why would I want to put it in a DTB versus just having it in tbbrcord.c as it is today, right? What should my motivation be today to move to using the DTB?
So you can add the descriptors over there. You can form the chain of trust in the DTB and provide that information in the device tree over, right?
I think Raghu lost connection.
I think the point is that there's no added benefit for now to move to this specific.
So, so I think
doesn't it improve the reuse of the code?
And even it is a readability of the code also will get increased. That's what I mean to say. This because you get the proper idea of how this code are being formed and right.
so. The way we first thought about this is, there's always a cost to be paid for making it more dynamic. So the cost could be in terms of more cycles that you take to load up, or the cost could be more memory requirements. So not all platforms will be willing to pay that cost. So Linux can afford to do it, I guess, because it has a lot of memory available. Now the immediate benefit I see is suppose you have a related platform or even two platforms which need to load two different sets of images. For example, one platform doesn't have BL32 and the other platform has BL32. So previously we needed to recompile the entire firmware and reflash the whole firmware to the board. But now all you need to do is replace the configuration file, and the firmware images can be the same. So by just changing the data, you can enable multiple related platforms, but slight differences to be run. But I agree, it doesn't go all the way to having a single firmware image, but it's still useful for related platforms. Like for example, if Allwinner, I think Allwinner is using device tree configuration, and the only difference they have between the different Allwinner boards is some UART that is being used. So they can still have single BL31 image and then describe the UART differently. And only the configuration file is different over there.
Right.
But I think...
So, wait, sorry.
Yeah, so there is the ideal goal of having one firmware image, but as I see it, there is a cost to be paid, and it's not clear whether all the platforms are willing to pay that cost. That's the thing.
Right. So where your argument would not hold is when you enable secure boot, right? So imagine you're signing the entire FIP image. Now we're going to be signing the DTBs. As soon as you modify the DTBs for different variations of platforms, yeah, now you still have two separately signed images.
Yes, yes. So
right. So a firmware update would still be a full update of FIP.
Yeah, I guess we could compartmentalize the images. Like you can have one FIP having all the BL images, and another FIP having the DTBs. So you just update the DTB FIP, whereas the original FIP can remain the same. Yeah, but I agree there are still limitations, but it's we have to see how much further we can take this. But I agree, it will be good if we can reach a place where all you need is a configuration file and any build of firmware will just run on your platform. Yeah.
All right. Yeah. This has. I see a lot of value for it. Right. If we do this, yeah, I guess FIP having two FIPs is one solution to it. Right. If you have that, yeah, I see it having a lot of value and giving a lot of flexibility. So yeah, that's just something to keep in mind. Thanks.
Yeah.
Yeah. So folks, we've run out of time, unfortunately. Great discussions, and as always with the TFA code base, there's lots of options and lots of capabilities that we're trying to add, and it may not be for everybody and every platform, but our hope is to evolve the TFA code base to newer designs and newer approaches, while also trying to, of course, maintain backward compatibility to all the upstream platforms as well as we can. Unfortunately, we don't have any time to go through the mailing list this week. But I would ask folks if they want to follow up on anything that they were hoping to say today, please do that on the mailing list again. We do monitor that. And also any new discussions that folks want to do from the discussions we've had today. Please use the mailing list to kick off discussions, and we will endeavour to follow up with everybody. So thank you, Manish. Thank you, Nadug. And thank you for everybody who's joined the call today.
Thank you. Bye.
Thank you. Bye-bye, everyone.
Thank you. Bye.
Thank you.